All right, so then we'll start the program for today, and it's great to have as a first speaker Michael Goldstein, who will tell us about uncertainty analysis for complex systems modeled by computer simulations. Please.
Fine, well, thank you very much. It's a pleasure to be here. I think my topic is in the mainstream of what we're talking about. So I was asked to give a kind of an overview, introductory, tutorial-y thing for the kind of things I do. So let's do that. So as we've already seen and as we will see throughout the workshop, most large and complex systems, there are models, there are data, there's a variety of things to do. Let's give a bunch of examples. So oil reservoirs, we had a little bit about that yesterday, about sort of what happens under the ground and how it relates to what we see above. Natural hazards, floods, volcanoes, they're looked at by modelling. Climate change, obviously modelling. Galaxy formation, what we think we know about the universe, people build models, Big Bang to now, and compare them to the universe. Disease modelling, again we saw some of that yesterday, and we model diseases to hopefully intervene positively. Energy planning, all of the investments that people make, the constructions they do, they're all driven by models. So these things are all very different, and the reason I put them all up is to make 2 points. Firstly, they're all very different. Secondly, because I'm quite old, I've been involved in all of these. So each one of these I've sat in the rooms with the scientists and we've published papers. So I have enough authority, I think, to say that even though the science is completely different in each case, the underlying methodology for handling uncertainty is the same. And that's why there is actually a subject that we're talking about. And some of the things I say will be effectively reflecting on the fact that I sort of whittle away things that don't work in particular areas, and things that continue to work are the ones that I keep. Okay, so let's just jump straight in. So there are many ways to get your head into this. I think a good way is to start by thinking of a very simple example, see what you would do for that, and then see what is difficult about that, and then see how you'd overcome that. So here's a really simple example. Okay, so there's a single input, a single output. We're looking at the concentration of a chemical which evolves in time. So we have a function for it, we do a model, we write down a differential equation for it. It involves a rate parameter which we'd like to learn about. As it happens, we can solve this one. So that will be useful for what I'm going to show you. Obviously, any time when we back out a methodology, we can't rely on that solution. Okay? But anyway, so here we go. I'd like to thank Ian Vernon, who created all these great pictures, and I think they're very instructive to help see what's going on. So time on the x-axis, concentration on the y-axis, 5 different runs for different choices of concentration parameter. We want to learn about the concentration parameters, so we just take a measurement. We're going to take a measurement at time t is 3.5. The measurement will have error. So how do we translate the measurement into understanding about the rate parameter? Well, a natural way of doing it is to throw away everything in the picture apart from what's happening at 3.5. There we do that. Okay? And we now replot it in that way. So now the rate parameter goes along the x-axis and the concentration at time 3.5 goes up. We've put the observation that we made is a big black line, and these sort of error bars on it, the dots. Okay, and so because we can actually solve the equation, let's actually put it in the solution, and there we see it. Okay, so effectively, I mean, there are many nuances that you can build on top of that, but basically, we're in that green region. Okay, and that's what the measurement told us. We're probably nearer the center, but that's the picture. If we continue with this, let's suppose why did we want to know about this? Because this was in fact an important concentration, and we want to measure it through time. So let's think about forecasting. Beforehand, it could have gone anywhere. Now we've seen that observation, that restricts it. Okay? So by doing runs, the observation has basically improved our forecast about what would happen. Now the example is simple enough that that's all there is to say really, but on the other hand, in more always we want to go into the future, And often there will be interventions that we could do. So we would like that concentration to be high, and you could maybe imagine that there's some other dial that we could turn. So if we did that, we would be then looking at our decision choices. We want to optimize our output, and we would find an optimum that behaves well, basically in that region. Okay? So that's a method. So we could say, you know, if we only did functions like that, then that would be the end. There wouldn't be any workshops. We just go home and we just do that. But so what's the problem? There are three basic problems. Okay? And all of the methodology, I think, is about overcoming these three problems. So let's just go back. I mean, the whole thing worked because basically we could draw that line. Yep. So the first problem is that we can't draw that curve. Okay, so it's too expensive to evaluate the computer function everywhere. It's just too hard to do because, you know, in all these models you can't just go bang, you can't solve the equations and draw it. You can't do that. So I believe that's the second workshop is going to be all about that. The second thing is that even if I could draw that, see, that was dead easy to do the inversion, but real inversion is obviously much harder. Okay, so the second thing is that even if we could do that, we couldn't do the inversion because the model has many inputs, many outputs. Each one of the inputs is like a complicated thing, and you're inverting the whole lot. That's hard. I believe that's workshop number 4. Even if you could do the inversion, it would still be really hard to optimize your policy because that's another whole bag of worms. That's kind of workshop 3, I think. I'm not sure about that, but anyway. Okay. So those are two fundamental problems. Okay. So we can't draw the curve, we can't do the inversion, and we can't optimize. Let's suppose that we could overcome those. We then hit the third problem, which was even if we did the inversion and the optimization, that would tell us what the model tells, the data tells us about the model, how to make life good for people in the model. It would not tell us what's happening in the world and how to make things good for people in the world, because the model is a model and the world is a world. Now that's not actually a workshop, but I'm hoping, I mean you can already see in some of the talks in day 1 that people were putting in the notion that the model is not the same as the world. And I hope that it's not a workshop because it's so integrated into everything we do that, you know, that we're just going to keep taking that on. But it is a fundamental problem. Okay? So again I say different physical models are different, but the approaches for these 3 problems, drawing the curve, doing the inversion, and optimizing in relation to the world, that's effectively the methodology of this subject to me. And that's why there's a common underlying methodology, which is what I'm high level talking about. Obviously, you know, there are so many sides to all of this. So I think because we're early on in the workshop, and we're doing high level, I think it's worth talking a bit about what it is we are doing when we do an uncertainty analysis. Okay? Because uncertainty is a mysterious thing. And we see a bit of Richard's talk yesterday. I mean, people disagreed about what it even was that we were talking about, and that's an important point. So let's see what I think what my next curve is. Okay. So let me just give an example. So let's see a project called Rapid Watch. So Rapid Watch was rapid climate change, which was funded by the NERC. They put a bunch of so the meridian overturning circulation is that part of the Gulf Stream that carries heat around from the tropics to around here, drops it and then curves around. It could stop because some simple models make it stop. If it stopped, that would be very bad, and it could happen quite fast. And open question is whether historically, you know, in the past it has stopped, and then when it stops, many of the features, I mean, it's not easy for it to start again. It is arguable that many of the things we're doing to mess up climate could cause that to happen. There's a lot of controversy. People say, no, it could never stop. Wow, and everything, yep. So they put these arrays down, and it's kind of interesting. So I was part of this project. It's a great project. And so apparently, so they measure the path. So circulation comes up. You know, the heat carries on. It drops. It goes down, and the rapid watch arrays are at the sort of underneath. And for a few months during the project, it actually did stop. There was no passage at all past the arrays. I was surprised it never made the papers. And people say, well, that's a bit funny. It's not going. And then it started again. Phew. But so the notion that these things, huge changes are possible, is possible. Yeah? So anyway, so the question that Rapid Watch was meant to answer was the probability of rapid change in the MOC. Okay, so now I'm an uncertainty quantifier, and I think, do I know what that means? The probability of rapid change in the MOC. Okay, does it fit into any of the categories? Do I know? I mean, if for no other reason than that the probability change depends on what we do. I mean, is there a notion of the probability of rapid change in the MOC? Do I know what that means? No, I don't actually. Here's what we have to do. So there's a whole bunch of things in the Rapid Watch program, and the one that stood out to me is, okay, so Peter Challoner was sort of going to run the sort of oversee the whole project, and I was kind of doing the statsy bit with Danny Williamson, and our job was to make sound statistical inferences about the real climate system. So I put this up quite often, and I say, as a joke, well, obviously I don't want to make unsound statistical inferences about the fake climate system. That would be a stupid thing to say. However, what is a sound statistical inference about the real climate system? Can you show me any previous sound statistical inferences about the real climate system ever, and explain to me what made them sound? I have no idea. And I put these things up because they're sort of in the wash of uncertainty quantifiers. We put stuff up like that. But now, here's a point I want to make. I put these up when I give talks to climate people, uncertainty quantification conferences, and etc. And maybe this meeting will be different, but nobody's ever said, well, you're a dope. It's obvious what these things mean. Yeah, but I mean, how can you, claiming to know about uncertainty quantification, not know what a sound inference about the real climate system is? You stupid. And how can you not know about the probability? It's because we don't know what these things mean. We share, and certainly on the project, it was a great project. Hopefully we made good contributions to science, but nobody, in the end, nobody asked us to make sound statistical inferences about the real climate. We certainly, my starting pitch was that there's no such thing as the probability of rapid change in the MOC. No one seemed to mind. The science carries on. But the point is that it's very unclear often what we mean when we make uncertainty statements, which is worrying because we then transfer them to other people who assume that we knew what they meant and then use them to make policy and determine people's lives. So a small digression on foundations. So Jimmy Savage, it was about 60 years ago, he wrote this wonderful book, The Foundations of Statistics. And here's a good quote. It is often argued academically that no science can be more secure than the foundations, and that if there's controversy on the foundations, there must be even greater controversy at the higher parts of science. And then he goes on to say, well, that doesn't actually appear to be true. In fact, there's huge controversy about the foundations, but that doesn't just go on and they just do stuff. Like the people in Rapid Watch, they weren't paralysed by not knowing what the words meant. They just did their usual science. But he goes on and says, here's another, it's a great book, it's full of great quotes. It is unanimously agreed that statistics depend somehow on probability, but as to what probability is and how it is connected with statistics, there has seldom been such complete disagreement and breakdown of communication since the Tower of Babel. Okay? So that's quite good. So, okay, that was 60 years ago. So has that all been sorted out? Do we say, oh, well, that was in the past, now we all agree and we know? I don't think so. I mean, I still have no idea what other people mean when they talk about uncertainty. So let's just say this. Just put the case out here. Okay, so we are involved with big modelling exercises, big data sets, etc. And our assessment of uncertainty is crucial. But until we know what our uncertainty statements mean, it's hard to know why it's crucial. So I can't make a sound statistical inference about the real climate system until I'm clear what those are. And it's certainly the case that most climate scientists, if you ask them what they mean by uncertainty, would say, well, they would not give you a crisp answer. It's like if there was a dog over there, okay, and it looked quite fierce to me, but someone said, no, you can stand next to it, it's okay. The probability that it will bite you is very small. I'd like to say, what exactly are you telling me? It looks quite yappy to me. Wow! I want to know what information is being conveyed. It's a fair question, surely. Yeah, okay. So let's just quickly run through the meaning of an uncertainty statement. Some people try to say, well, no, it's a property of the world. There is a real thing, the probability that that dog will bite me, and it really is small. Okay, and relative frequencies try to capture that. Okay. There's another way of people think about it as logical. So there's a logical bunch of relations, and it is logically true that that dog in some sense won't bite you. And it's interesting philosophically whether there are such things as true probabilities or logical probabilities. But by the time we get to the complexity of the models that we're looking at, so Richard yesterday gave us an urn, and we were still struggling to agree what we thought about that. But by the time you're getting into climate change, to energy policy, etc., you're so far away from the notion of these things that really I think they're no longer helpful. So I'm a Bayesian statistician. So in principle this is straightforward. Probabilities are the judgments of individuals. So not the probability that the dog will bite me, but Anne's probability or Bob's probability, which may be different. So effectively the power of the Bayesian argument isn't that it gets Anne and Bob right, but it gives them a way of putting together, in order to reach that judgment, it can synthesize all of the things that are involved in judging whether that dog's going to bite me or not. And the Bayesian approach has many excellent tools to help Anne and Bob. And if they do differ, it gives them many tools to explore that disagreement. So it's clearly doing a useful thing. And in computer modeling, it's pretty well established. It feeds naturally into decision making. So all of these things are so I'm Bayesian. The Bayesian approach is very good. Okay. Let me make one caveat to that, however, because we're still at the early stage of talking about what it is that we mean about what it is. Okay. So when I'm told that the probability that the dog will bite me is very small, now it might be because it's a dog and which isn't a made-up example that, in fact, Anne would say, yes, actually, that's my opinion. Most likely, though, in science, that's not the case. Okay, anyway, sorry, there are good pragmatic methods, okay? That in practice, when I read a Bayesian analysis of a scientific problem at the level of what we're talking about, how do you invest in energy policy, how do you do this, how do you do that, it's very rare to see a Bayesian analysis and say, what does it mean? Well, it's Anne's judgment. Okay? But what happens is that there is some model, there is some prior that's chosen for semi-pragmatic reasons, there are complicated MC calculation, there's an answer, but if you say whose judgment does that represent, who's going to stand by it, I've never seen anyone actually stand by a judgment that they've actually put up on the board. And I ask them, is that your actual judgment? They say, well, no, kind of, not really. It's just it's a Bayesian analysis, like any other stats analysis. Okay. And fundamentally, it's because when you get up to the level of things like climate change, the amount of careful work that would be required in order for this to be effectively the Bayes paradigm to really apply is just beyond the ability of the person who is supposed to sort of inherit the judgment. So the reason that they step back from it is that they're very aware of what they didn't do, which is understandable. But on the other hand, it does mean then that what looks like a very clear difference between Bayes and the other things is not so clear. Bayes has again been used as a model, and so uncertainty statements have been happening in the model, and all these models, logical probability, relative frequency probability, Bayes, are very, very useful models. And models, I mean, after all, everything's about models. Models are terrific, but a model is a model. The world is a world. I want to know whether that dog is actually going to bite me, and until you make that translation, this is not clear. So one thing I hope is that when people put up uncertainties about the world, they're clear what they mean. They say, it's my judgment, or it is a logical statement, or it is an underlying, or just something. Just be clear about what it is, because we're not clear, and I don't know what people are trying to convey to me when they put uncertainty statements up. So yeah, okay? Anyway, so while I'm conscious that time's going to run out before I even get to anywhere, but for these reasons, even though I say I'm a Bayesian, I'm just going to tell you that there are different ways of being a Bayesian. So, as I said, it's hard because the level of detail that you require is just beyond people's ability to do. So the Bayes linear approach is like Bayes, but you take probability as a primitive, which is a very clumsy primitive in my view, because you have to specify everything, every possible thing that could happen in every combination at extreme level of detail. You replace it by expectation as a primitive, which means you think about those expectations which to you seem relevant and you're able to specify. Okay? So the approach, I always say, is similar in spirit to full Bayes, uses a much simpler approach for specification and analysis, and so offers a practical methodology for analysing partially specified beliefs for large problems. So all the examples I put at the beginning, when we come to it, they were all done in a Bayes linear way and look fine to me. So Jim put this thing up as a side comment on his slide yesterday, and I agree with that. If you're coming from a full Bayes perspective, but you're overwhelmed by the complexity of the calculations, this is a good approximation. To me, I don't see it that way at all. I think that there are fundamental foundational reasons why this is the right thing to do, and it's not just an approximation, because it's all it's an approximation to is a model. But you actually make actual judgments through your expectations, and so the Bayes linear thing gives you the appropriate method for analysing these things. Obviously that's a large question, but if anyone is interested in the foundational questions about how you should analyse your beliefs, I'll give references, and if you don't want to talk to me, because obviously it's interesting, I'm happy to talk about it, endlessly. Okay? So let me just put, so Bayes theorem, Bayes analysis runs off a single theorem, Bayes theorem, Bayes linear adjusted expectation and variance. So there's y you want to learn about, z you observe. There are simple equations, okay? And why they are the approach, you'll recognize them. People who Krieg, people who do lots of things tend to use these equations. And fundamentally the reason that they work is because sitting underneath it is the notion of how expectations are modified and how you project between things. But anyway, so the reason I'm not going to talk about computation anywhere in what I do is because we do, our computations are straightforward. There's a book which tells you everything you could possibly want to know. There's a very quick reference, only 7 pages, in the Wiley Stats Ref, and if you're interested in it just pragmatically, what would it mean me actually doing this for my problems, every paper for every application, effectively we do it in a Bayes linear way, which is why computation is not a big feature of what we do. And you can judge our success because, well, we'll talk about that. Anyway, so let's get back to the problem at last. We have a simulator which takes an input x, which is unknown parameters, and d, which are design things that you can do, and it gives an output vector with system behavior. You want to choose appropriate x inputs. You want to use historical observations to test and constrain your model, and that so the historical observations correspond to some subset of the things. You want to ask how informative this model is going to be for real system behavior, and you want to make a best assignment. And typically, it's expensive to evaluate the function. Doing that inversion is hard, getting good decisions is hard, and relating the model to the world is challenging. So that's the world we're in. So, well, we've already heard a lot about, okay, so the first thing, the model is hard, expensive to evaluate, so we emulate it. You've already seen people emulating already, and I think probably in each workshop people are going to be emulating like crazy things, because that's the way that we overcome the expense of the function. We make some evaluations, we replace by a meta model. Okay? So we treat the function as uncertain, and we're now talking to me, I'm a Bayesian, about my uncertainty about the function. I know it at a certain small subset, I don't know it everywhere else. So we construct a description of the uncertainty. That tends to be called an emulator. Slightly misleading terminology, I think, is my uncertainty judgment, but people like to think of it as a thing. And the emulator contains an approximation to the simulator and an assessment of the magnitude of the error. And unlike the function, which is slow to evaluate, the emulator is fast. So all the things you wanted to do, I can't draw the curve in with the model, I can draw the curve with the emulator. That's the idea. What does the emulator look like? You've already seen some of them. So I take a particular output, like maybe the concentration at time 4 for the rate parameter, and basically I break it up into the part, well, let's put these things up here. Okay, I put it up into a global part. Okay, I like to think of it as a global variation and local variation. So I fit a deterministic curve, and I fit a residual. Okay? So the deterministic curve, for example, it could be a polynomial fit, is global because wherever you put points, they tell you about the global fit. The u of x is the residual, so f of x is continuous, so the difference between f of x and my deterministic fit is again a continuous function. Okay, so we have various models for continuous functions which are smooth. So if u of x is small and positive at a particular choice of x, if I move x just a little bit, it will still be small and positive, but maybe we can go up a bit or it'll go down a bit, and the strength of the correlation determines how quickly that changes. But so that's basically the picture. Okay? Now, people talk about Gaussian process residuals, or people talk about, because I'm not thinking about full distributions, I just think about second order stationary distributions. Now again, a quick comment about the difference between an emulator being a thing and it being a judgment. People say, well, this can't be right because our model is not a realization of a Gaussian process, but what that actually encapsulates effectively is my uncertainty judgments, and we could talk about that offline because I'm not going to have time to talk about that, but effectively it incorporates my exchangeability judgments. What it's saying here is that my uncertainty about two things that are equally far apart doesn't matter where you choose them. I mean, that collection of things is exchangeable, and that leads me to this construction. And of course, they're not exchangeable until I've put in my deterministic model. Now, the difference between different people's ways they fit emulators is really largely up to how much effort they put into the global part of the model. We tend to put a lot of effort into that for a bunch of reasons that we'll get to. But anyway, let's just do it. Okay, if you haven't seen it, okay, here's the curve. Let's take the curve away. There we go. So here's our emulator. Now we're very careful not to fall into the trap shown in Jim's example. So we need to talk about how we don't get a really stupid emulator, but there's our emulator. Okay, so the blue line is our expectation. The red line is our uncertainty bounds, and there's our observation. And so there, so we now do it through, we have extra uncertainty obviously because we don't know where the line is, but we can still do the inversion with more uncertainty. Okay, so the emulator takes us through. So how do we emulate? Everybody has their own method. There's everybody, as soon as they start doing it, writes an R package, and they're all really useful. So let me just say a little bit about what we like to do. Okay. So we like to, well, if possible, you put down a space-filling design. We've talked a bit about that, what you've heard talks, and I think Henry's going to talk a lot about this, I suspect, okay, which for different ways of thinking about this. So we do that. So we have a design where we make lots of runs of the model, and from the runs of the model we then fit our emulator. It's a time series, it's lots of things, there's lots of outputs. So we decide what we want to emulate, and these may be individual outputs, they may be combinations, they may, if it's a time series, it might be, for example, the maximum. If it was an oil reservoir, it might be the first time at which water sort of enters your system. Yeah. So you choose what to emulate, and for each of the emulators, you aim to identify what are the driving features. It's very important to us to think what are the fundamental things that these things depend on. We build our emulator basically, our deterministic part is on the things that are most important. Our residual, I didn't actually write it in there, but we often split that into two parts. A Gaussian, let's say a Gaussian process on the active quantities, and then a further residual on everything else that we haven't put in, which of course raises an interesting point. People like emulators because they interpolate. Interpolation, in fact, is a very bad property. If I have 200 inputs, but I'm only really driven by 20, I would like to actually make that a function of 20 and just say that there's some residual error that's to do with the 180 that I haven't measured. So my thing will no longer interpolate, but it will mean that I've turned a 200-dimensional problem into a 20-dimensional problem. So often our emulators do not interpolate, and I think that's good. Okay, so how do we do this? You can do it all in one go, and that's hugely dangerous. We tend to prefer to fit the global form and then fit the local form to the residuals. So you bang it in, okay, you find the appropriate curves, and when you do that, and part of that is, time is running out, but let me just show you. So imagine here's x and here's f of x. Maybe the points look like that. Okay, then obviously I'd like to draw that line as my mean and say that my function is basically, it's flat there, and there's my residual is basically has a small variance and a little correlation. Yeah, but on the other hand, particularly if I'm doing a Bayes fit, then that's going to pick up. I have lots of independent things that are telling me this doesn't really look very normal. Maybe they're not very normal. So I could get another fit that will be way down here. Okay, so and then I have very big variance. So my emulator says now, no, the mean curve goes down here, and I've got my residual term has a huge variance and a very strong correlation. Yeah, and that's going to be just a bad fit. Everything you do with it later on is going to mess that up. Yeah, so therefore we think if this is what you want, fit the mean first, take out the residuals, and then fit to the residuals. It's estimating things like correlation parameters and stuff is twitchy. Everything's linked. So our strong suggestion is to do the global one first, and that's one of the reasons we fit quite complex global surfaces, because it takes out the twitchiness of the Gaussian process fit. You then make a look at the scientific plausibility. Does it seem plausible to the expert that we've chosen the right active variables and they're doing the right kind of things? So we look carefully at the global components that were fitted. We then do diagnostics, as we've said. You take out, you make a prediction at a new point. Does it fit? Now, the big issues in any of these model fitting are between interpolation and extrapolation. In high-dimensional problems, you're mostly extrapolating, because once you however many points you put in, mostly the area is outside. So you can be sensible about that. You've drawn your curve. So this is how you do diagnostics. There's x, here's f of x, here's maybe my curve looks like that, but I've only actually got observations up to here. Why am I not going over there? Because of course in the real problem x is like 200 dimensional, and I'm looking at a whole bunch of these pictures, so I see in fact, well, maybe it goes right the way out there, out there. Okay. One of the reasons we fit the Gaussian, our deterministic part, is because if we don't fit the Gaussian process, if we didn't put that curve in, it wouldn't know to go out that way. So the Gaussian process will be good at following this. It becomes lousy outside. However, extrapolation has a risk, but this is what our diagnostics are. We look at our key points here. We say, oh well, I better evaluate a point here, and I better evaluate a point here. So our diagnostics are chosen basically. Interpolations won't be so bad to test our extrapolations, and as long as you do that, then you can validate your emulator. That's how you do it. And again, emulation can be quite difficult. Some outputs will be easy to emulate, typically. Some will be hard to emulate. We'll talk about that later on. Well, if I keep racking on. Okay, so you need a lot of observations to do the emulation. Supposing you haven't got them, then this is what we do. You create a fast approximation to the simulator, use lots of runs on the fast approximation, so you can build an emulator on that using what we've just said, and then you then have a design problem of you can make a small number of runs on the expensive emulator, expect a simulator to build your emulator, and it's an interesting design problem of how do you choose those runs. So the key driving force to me of design for uncertainty quantification is when you can only put a small number of design points down. You're designing for many, many different outputs. Each output has its own peculiar structure, and you have a single design that has to work for every one of the outputs. So I'll give a reference to what our thoughts about that, but you can see that there's a subject and that there are interesting design questions, and that you can get interesting solutions to those. And as I said, I'll put references up at the end about how we might do that. And again, someone who's building simulators that they want to use them in order to help people understand the world. If their simulators take a long time to run, they should provide methods for coarsening the grids, cheating on the step size, doing all the things that would make it run faster to allow you to do this. Now, okay, quickly going on. Fitting simulators to data. Okay, I can now emulate. So that's drawing the curve. So simulator calibration aims to identify the best choice of inputs, okay, based on matching data. Okay. Now, I'm very suspicious of that for three reasons. Firstly, it's a model. The idea about finding the true input choice is a fantasy. There is no true input choice. It's a model. Most of the x's that go into these things are hypothetical constructs. There is no real world equivalent. There is no sense of saying what is the correct fudge factor for making water look like treacle so that a climate model will run. You have to put one in, but the notion that there is a true correct value, there is no, so the infectivity in a disease model, that infectivity is a simplification of a complicated, time-varying, human-varying thing. There is no, these things they're not. Okay, so we have a problem in the idea that we are going to find the best one. Okay, there may be no good choices. It's a model. It could be a bad model. Even if we wanted to do the probabilistic calculation, it's hard and it's horrible. It's hugely non-robust because it works because probabilistic Bayes, it does all the things I don't like. It does point-wise. You put your point sort of likelihood times your point prior, two things you didn't even really think about very hard. They get multiplied together, and arbitrarily some will be bigger than others. You have huge ridged, terrible likelihood surfaces. It's a very sensitive, complicated operation for something that's not even clear to me that it means anything. So we prefer to do history matching. So in history matching, you don't ask what's true. You say, what are the choices of inputs which, if you ran the model at those inputs, would make the output look like the history that you've actually observed, up to all the errors in the problem. Okay? So if you observed at certain time points certain phenomena, a history match would be a choice of input which, when you run the simulator, gives you an output which roughly matches within uncertainty to these things. Okay, then typically we find that there's a tiny, tiny fraction of your input space that corresponds to this. So, and it's always interesting to look at that. It could even be empty, of course. I mean, that would be a big warning to you. Okay, and what we then do is we say you reduce to that reduced region, and then basically you find things which, if you have to do a forward choice, which are reliable across all those choices. Okay, so let's do it. I mean, I've shown you history matching already. That was history matching. The green choices of X roughly matched what we actually saw. The red choices clearly didn't. They were just bad choices. Okay, so now what we do is, it's easy enough in a one-dimensional thing. How do we do it for high dimensions? Well, there's our implausibility measure. So we look at, so there's Z, which is the black line. We compare it to the blue line. So we look at the distance between the two of those, and we calibrate it basically by the sort of the variance. So how we add up all the errors, and then we want to stay within the error bars of that. Okay? So that's history matching. Okay? Okay? So, of course, I just did it for a single output, but you can do it over as many outputs as you like. and you basically remove the ones which are bad matches. Okay? And the key point about history matching is that it's a very flexible tool. You do it once, you remove space, and then you do it again, and you keep refitting. And it's easiest to show in the picture. Here's as we got to that point, do we stop? No. Once we think, oh wait a minute, so X is going to be in the green bit, we make more observations in the green bit, we refit, so we re-emulate in the green bit, and we then re-history match. So the whole power of the thing is we don't go for the good fits, we remove bad fits, we resample, and we re-emulate, and we continue. Okay? So notice that it's very hard to emulate a real model over a big space. It's not so hard to emulate a model well in a small space. So the whole point about this is that we only need to produce good emulators in the regions close to the matches. So everything we do is focusing our attention of careful emulation to the later stages. So when I said you can't emulate everything in the beginning, that's fine. Things which are impossible to emulate in the big space, as you reduce your space, tend to become easier to emulate. So gradually we introduce more features. Okay? So it's a flexible tool, and it works, to me, it works very well. Even if you wanted to do a calibration exercise, I strongly recommend you try doing a history matching exercise first to reduce the space, because if the original space is tiny, it will be hard to find it by an MCMC method. Oh, I have an example here, just because it's boring not to have any examples here, so let me just quickly say, so it's an HIV modelling example. The simulator is Mequano. It simulates people being born, they meet people, they form sexual partnerships, they have sex, they get ill, they leave the partnership, they have sex with somebody else, they leave that partnership, they die. It's quite a poignant model, okay? And yep, so you can imagine it has a lot of parameters. It's a stochastic agent-based version of the model you were showing yesterday for infectivity. And the interesting thing about this model is that it matches a really rich data set. There's a region in southwest Uganda which has residents of 25 villages, and since 1989, every year, detailed demographic and infectivity information has been taken. Okay, so we really have an idea about what is happening in this region. So when we fit our models, this is a great test bed. Okay, so there are a bunch of things. There's population sizes, there's prevalences of HIV, and etc. Okay, and it takes between 10 minutes and 3 hours for a single one for this model. So there's a reference. You see, I'm a small cog in this big machine, and doing history matching. Okay, yeah. There's a more careful and detailed example where we make a larger model for this in the Siam Journal of Uncertainty Quantification. Again, we history match. Okay, and the reasons for doing that, it's a good place to look. So just quickly some details. I haven't got time to talk about this very much, but look. So we create our Latin hypercubes, we create emulators, we go up to cubics, we validate them apart from a couple that don't get validated in wave 1, but they'll come back later on. We do our history match. You see the history match didn't take very long. It took about 5 minutes. On our first wave we go down to 10 to the minus 5 of the original space. We do a certain number of, in fact we go through 10 waves of refitting. Again, huge amount we could say about that. This is the kind of picture that we like to show. There's year across. There's one of the outputs is male HIV prevalence. So the computer model calculates it every year. So red are the outputs from wave 1. You can see they're hopeless. They have huge prevalences. They're all over the place. By the time we get to wave 4, they're not looking quite so bad, but they're still way off. Wave 6, you know, they're getting there. By the time we get to wave 8, we can see the green ones are mainly getting there. Okay. Now remember, you're just seeing 3 out of the 18 that we're matching, and so by the time we get to 10 waves, we're down to about 10 to the minus 11 of the original space, and around 65% of the evaluations in the final wave match the data. So, so if people want to say, can you show me the kind of parameters which are supported by this model? There you go. So when people then think about interventions, they want interventions which are good in that small subspace. Right, very, very quickly talk, so time is right past, about the limitations of models. It's my final topic. So, a model is how the system properties influence system behavior. Okay, this is the properties of the inputs, the behavior of the outputs. So there's two simplifications of every model makes. We approximate the system properties, obviously, because they're too complicated and we don't know them. We approximate the rules for going from properties to behavior, because they're too complicated, we don't know them, we couldn't calculate them numerically anyway. So we make these approximations, and that's what modeling is. It is simplifying so that we can take the real world, which is too complicated, in doing stuff, and it's fine, but the only problem arises when we forget that we've made these simplifications and we treat our statement about, from the model as if it is a statement about the world. As if we say, well, okay, now in our disease model, you can now do this intervention and these lives will be saved. It's not as simple as that, obviously, and it's important to be clear, are you still living in model world? How have you linked it to the real world? So in principle it's easy. I mean, all that model discrepancy does is it adds uncertainty around sort of my original curve here, but instead of around the observation, it goes around the curve itself. But we can imagine how we can use it, so history matching takes it very easily. The question is, how do we construct that purple curve? How do we put sensible numbers on? Obviously, we could have a workshop on this. Hugely important topic. So all I'm going to say is that we have a structured method for doing this. It's very important not to just faff about, you need to be organized in doing this. So we tend to view, I always mean I, but a lot of people a lot of my collaborators, some of whom will come up on the references, tend to go along with this, okay, is we divide our structural uncertainty, the difference between the model and the world, into two distinct features, internal and external discrepancy. Okay, I'm going to have one slide on each. Okay, so internal discrepancy is any aspect of discrepancy you can assess by direct experiments on the computer simulator. You might think, well, how could I do that? Here's a bunch of things. The model may have a standard forcing function. We could vary it. The model may propagate a state vector using very strict rules. We could introduce a bit of noise, say, well, that's a little bit too strict. Can we introduce noise into the propagation of the state vector? Parameters that we're holding fixed over time, we could allow them to be temporarily sort of like time varying. So there are things that we can do on by intervening in the computer model itself. Okay? So what we do is we hold certain parameters, we make certain choices of our input parameters. We do repeat experiments where we vary the things we want to vary. We get a notion of the internal discrepancy variance at those individual points. It could be roughly the same everywhere. Good, we have an internal discrepancy variance. Usually it won't be. So we take our internal discrepancy variance is now a function of our input parameters. It's an expensive function, so we emulate it. Okay, so that's another use of emulation. And again, is this going to be easy or is it going to be hard? A person who builds a simulator who wants to explore the real world should make this easy for us. Okay, that should be part of their construction of the thing. Okay? So there's internal discrepancy. It gives you a full joint distribution of discrepancy in the past and discrepancy in the future. It's a strong tool, and I strongly recommend you do this. It's natural. Then, of course, there are some things that can't cope with. If I've left out some basic processes, there is no way that I can, there's no experiment on there. So that's external discrepancy, so that's our second part. So external discrepancy is determined by a combination of expert judgment and statistical estimation. For example, if you think your model is great, but you've history matched and everywhere it misses by a large amount, there is some external discrepancy there. Okay. So you can just ask. You can just say, well, roughly, how wrong is it? And people always say 10%, but it's better to say 10% than to pretend your model is exactly right. It's much better to really go into detail about your understanding of the limitations of the model, to build a probabilistic representation of additional features, and to create that, often I call that process reification, because to reify is to treat an abstract concept as if it was real. So I explain to people that that's a mistake to treat your model as if it was real. But if you want to do that, what do you actually have to go through in order to take your model and have it tell you something about the world? Okay. Now, again, I'm going to, obviously I can't talk about it in a minute, but I will give you a reference as to how to think about this. And the reified simulator, you can't actually build the reified simulator, but you can emulate it. And everything, as we said, goes through emulation. So instead of history matching the emulator of your simulator, you history match through the emulator of the reified simulator, which is a bit mind-boggling, but in fact it's fine. In fact, it's good. Oh, okay, our time is running out, so there's this statement here about forecasting is being easy. So Z is your past observations. You want to learn about Y in the future. And this statement just says that you've actually got a joint distribution on everything. You have a joint distribution on the function because you've emulated everything. You have a joint distribution on discrepancy in the past and the future because of the methods that we told you will create that. And therefore, you can forecast the future from the past. And it's a very good method. It's very fast. It does the things that we claim, and we can talk about it. It corrects your overconfidence in the future because it puts proper uncertainty bounds on. It increases your accuracy because it corrects for systematic bias, and it helps to make reliable choices in the future because it recognizes the real uncertainties about the future. I'm going to skip the next bit. I'm so much into systems integration where there's many. Mostly now I work on models which join into other models, which join into other models. So clearly we can do that, but let me just jump that slide and make our concluding comments. So there is a general Bayesian method for performing detailed uncertainty analysis, which I zap through. Key features are emulation, we're happy with that. Structural discrepancy modeling, you should really think about that, and you should think that there are ways to do it. Okay? There's history matching, I strongly recommend you think about that, and obviously system optimization. And you should think about doing these things, you should think about what they mean, you should think about when you put an uncertainty statement into the world, what information you mean to convey by that. And if you're talking to people who are creating the simulators, you could say, look, these are all your jobs. When you build the simulator, make it easy for me to do these things. Okay, so there's that. Final slide of references. So the first one is, this is a way of crediting some of my collaborators, all these people who just do so much in this. Okay, so the first one is oil reservoirs. It's all the subsurface stuff we talked about yesterday, and it's a good one to look at for multi-level design. The second one is about floods, and again it's an overview. These are both overview tutorials, and it's good under showing you how to treat internal discrepancy. We talk about that quite carefully. The third one talks about external discrepancy, and there's a cute little example on the collapse of the MOC. The fourth one is where it's a whole universe, and it's very detailed, so that's interesting. And the final one is simply because, okay, I'm a subjective Bayesian, and I hope I've told you that's quite a nuanced thing, but it's important to think that there are good reasons for doing this, and that paper kind of lays them out. Oh, fine, thank you very much.
Thank you. Okay, thanks. Questions?
I have a question to the beginning of your talk where you introduced Bayesian linear analysis and based it on